Okay, I want to take just a minute to talk about Hooke's law. This sounds complicated, but it's really not. It's really just an equation to describe a type of force that we haven't talked about yet. And now that we're getting into energy, we're going to be talking about springs a lot, and Hooke's law deals with springs. So basically, Hooke's law is an equation that gives you the amount of force that an ideal spring is going to provide. Now, an ideal spring is sort of one that just by definition kind of fits this model. And a lot of things in nature are going to display this behavior, but nothing really displays it perfectly. So let me go ahead and talk about what it actually says. So basically, Hooke's law says that the force from an ideal spring is proportional to the amount that that spring is stretched or squished. In other words, this x value here, that's the displacement of the spring from its equilibrium position. So depending on how much it's stretched or squished, the force from it will be greater, proportionally to how much it's stretched or squished. This k value is known as the stiffness constant. So depending on like how stiff the spring is, you will get more or less force. So I think this is easier to see if we actually just look at an example. So here's a simulation, and actually let me pull this up just so we have somewhere to write, and maybe I will actually, let me make a whole new page to write on. There we go. Okay, so this is our Hooke's law right here. F is equal to kx. Now let's just see what happens when I apply a force to this. Right, so this spring has a spring constant of 500 newtons per meter. And notice the units there, right, newtons per meter. That makes sense, right, because this k value, right, if this is newtons and this is meters, then if we solve for k, we would have newtons over meters. So that's where that unit is coming from. So this spring that we're looking at has a spring constant of 500 newtons per meter. And now let's go ahead and apply a force to it, right? And let's make it so it actually shows us the spring force and shows us the displacement. And how about show us everything. So if we apply a force of, let's say 50 newtons, right? It's showing us right there that the spring is pulling backwards with 50 newtons of force if we displace it 0.1 meters. Right, so that makes sense if we just kind of use Hooke's law, right? The force, if our spring has a spring constant of 500 newtons per meter, and we displace it a distance of 0.1 meters, right? If we just work that out, we get a force of 50 newtons. Right, so now let's think about what happens if we double the displacement, right? So let's say we want to pull with 100 newtons of force, right? If we think about how far it's stretched, right? It's stretched a distance of 0.2 meters. So just to sort of check that Hooke's law is working, right? Again, we've got this spring constant that's 500 newtons per meter for this spring, and we're pulling at a displacement of 0.2 meters. And if we solve that out, right, we will get a force of 100 newtons out of the spring. So basically, the amount the spring stretches and the force the spring gives, they're proportional to each other. Right, so if we double the amount of force that we pull it with, we double the displacement of the spring. It also works the other way, right? So if we squish this spring, we get a force in the opposite direction, but still the force that we get is proportional to how far that spring is displaced from its equilibrium position. Right, the equilibrium position, we can see it, it's right there. Right, so that's where the spring is if there's no applied force to it. And let's see what happens if we change the spring constant. So let's go ahead and give 100 newtons of force. So we're pulling on the spring with 100 newtons. Now let's make a prediction about what's going to happen if we were to have a spring that has, let's say, double the spring constant. Right, so if we go back here to F equals kx, if we double the spring constant, but let's say we keep the force the same, we want to figure out how far the spring is going to be stretched. So if we solve for the stretch distance, That gives us F over K. Now, if we double the spring constant, oh no, right? If we double the spring constant, then, oops, right, the spring constant will go up by a factor of 2. That means the spring should stretch only half as much distance, right? Because if the spring constant is greater, the spring is basically stiffer. So it won't stretch as much under the same force. So let's go ahead and say we have a spring with double this much spring constant. Right, it's not stretched as far, it's stretched half the distance. So this is what Hooke's law is really all about, right? Just understanding this relationship. Oh, come on, let's go full screen. No. This is frustrating. Maybe I just have to get rid of it, then open it back up. Okay. All right, one other thing, often, I just want to point this out, is that for Hooke's law, right, often it's written this way with vectors and a negative sign. And that is just to tell you that the force that the spring applies is always in the opposite direction compared to its displacement, right? So in other words, if you pull the string to the right, if you move it to the right of its equilibrium position, the spring will pull and it will pull to the left, right? So if you have a spring and let's say this is its equilibrium position, this is where it would just be naturally. If you pull it to the right, so if you pull it to here, well, the spring will exert a force to the left. So if you displace, if the displacement from equilibrium is to the right, the force is to the left, and vice versa, right? So this negative sign is just there to tell you that the direction of these is opposite. So remember that x value, that's the displacement from the equilibrium. So that's how far the end of the spring is pushed from wherever it would hang out naturally. Maybe another useful thing is to kind of look at this other version of this simulation. This one actually shows us a graph, right? So we have, let's say we have a spring here, and it actually shows us that we have a linear relationship between the spring constant and the force applied by the spring. So it makes sense, right? Hooke's law shows us that there should be a linear relationship there, right? It's F equals kx. So if we graph displacement versus force, right, it makes sense that the slope of that graph will equal the spring constant, right? So we can actually kind of see what happens if we pull on this, right? We're actually looking at a different point on that graph, and I don't want to see energy. I don't know why it's showing me energy. We just want to look at the force. So yeah, don't worry about the energy graph over there on the right. We haven't really talked about that yet. Let's go ahead and look at the values. Right, so as we stretch this, right, as we increase the displacement from equilibrium, we get more force. Similarly, if we were to squish it, right, so that's registering as negative displacement, we get a proportional amount of force, but in the other direction, right? So now the spring is actually pushing to the right. If we change the spring constant, let's say we double the spring constant, so we make it a stiffer spring, notice that the slope of the graph increases. That makes sense because the slope is right there, right? So that just tells me that as we stretch or squish the spring will provide us with more force, right? If we double the spring constant, that means it will provide us with twice as much force. Okay, so that's kind of the gist of springs and Hooke's law. Hooke's law is just this equation. And remember that in real life, springs aren't going to obey this equation perfectly. The relationship between the force and the displacement isn't going to be perfectly linear. It's just kind of the way that we imagine it with ideal springs. All right, so I want to look at an example and just to kind of talk about how this can be related to work and what we're actually studying right now. So let's say we have a mass, and that mass is pressed back against a spring. The spring has a spring constant K. And let's say we know the distance it's compressed. And we want to figure out how fast will the mass be moving when it leaves the spring. It's actually a little typo right there. Can fix it. Come on. Okay, so if we want to do this using the work energy principle, remember the work energy principle is the total work on an object is equal to the change in kinetic energy of that object. And I know that work is force times distance. So in this case, that object is accelerating as a result of the spring that's pushing it, right? That spring is going to push it to the right and shoot it off. So if we were to do a free body diagram, right, we would have on the mass, we would have gravity down, normal force up, and a force from the spring to the right. And these two forces would do no work, right? So the only force doing work is the spring force. So if I write this in here, right, if I try to do the work, force times distance equals delta K. Delta K is K final minus K initial. The initial kinetic energy is 0. And then Kf is just 1/2 m times the final speed squared. Okay, but we have a problem. And the problem is that the force applied by the spring on the block, it changes as the block is being accelerated, right? So at first, the force is really strong, and then the force actually decreases over time, right? So if we were to try to draw the force over time, or not force over time, let's say force over distance, well, it would actually decrease because the force starts out really strong when the spring is squished. And then as the spring approaches its equilibrium position, it becomes shot off, right? So the spring starts out, it starts out very, very compressed. And as it moves over this displacement, the force decreases. So it actually would look something like this. It would actually decrease linearly because Hooke's law says that the spring force should be proportional to how far it is away from equilibrium. So this would be like the equilibrium position of the spring, and this is where it starts out. So in order to find the work that's done by the spring on that mass, we can't just take this multiplication. We would actually have to find the area under that graph, right? So we would actually have to find that area, and that would give us the work done by the spring, right? So we would actually have to get that. And it turns out it's actually a triangle. So if we actually wanted to solve it, we could do it because it would just be the area of a triangle is like 1/2 base times height. And the base, right, this distance is just, right, this is d. Maybe should have called that x or something. And the maximum force that it starts with, right, at the top, that amount of force that it has at the beginning is the maximum amount of spring force, right, the amount that it had right before we let it go. And that is equal to K times the initial displacement that it had from the equilibrium position, right, which was d. So we could actually write this as 1/2 kd times d, and that would be equal to 1/2 mv squared. So we can actually solve for the final speed, right? It would be kd squared over m square rooted is equal to v. So it's actually possible to find the work done by the spring force on that block by finding the area under the spring force on the block over the distance that the block travels, right? And remember, the spring force is starting out strong and it's decreasing as the spring shoots it off. That's why this graph is going down instead of up like the graphs we saw earlier. So I hope this video was helpful. Remember, kind of the main thing of this video was just wrapping our head around this equation for Hooke's law, which is this linear relationship between force and displacement of a spring. This example might have been a little tricky to wrap your head around, but I just wanted to explain that if you're trying to find work done by a spring, you can't simply do force times distance. You need to take into account that the force is changing, right, as the spring stretches or squishes, right? Here it's actually unsquishing, right? So you've got to actually find the area under that force versus position graph, right? This is the force on the block versus position as it's being shot off of that. So that's where this came from, right? This was the area of this triangle. So yeah, if you have questions, let me know. I hope this was helpful.